Hello everyone. Today in this video we are going to see how I designed a mobile robot with a differential drive and a spherical wheel in the front, and I'm also going to show you how to path plan it in this scene with the obstacles and how it moves from start to target. So before going into that, we are going to see actually how I designed this robot. For this, first I have taken each and every part. This part you can actually separate it.
STL.
Hmm?
STL.
It's an STL file where you can see that this is a scene hierarchy which has visible base and the left wheel, right wheel, and this is a wheel holder and this is a front wheel. If I simulate it, you can see that the robot is moving slowly forward because I haven't given any actuation in this. Uh, so in this robot has, as we can see in the scene hierarchy, has an invisible part and a visible part. This invisible part is actually the dynamic part. So before going into what is a dynamic part, we will see what are the considerations that is taking into into dynamic part. The first consideration is that it should for creating an invisible part, we have to convert the visible part into convex shapes, where we will find it in edit, where we will find it here, right, when we right click it and edit it and into morph into convex shapes. If we morph something into convex shapes, we can see it gets converted. I'll show you how this invisible part gets into a convex shapes. If I double click here, we can see it is in torque force mode. Hmm? The position is cyclic. Hmm? And
360 degree.
it rotates 360 degrees, and here the camera visibility is also given. It is because it is a motor, it does not have any collision special properties. And in dynamic properties we can see that it has a motor target velocity is there and torque is also there. We can also use this in by uh,
Control properties.
by using control properties. If we enable control properties, we go into PDI controller, which is basically used in PID controller, sorry. So here we can see that dynamic properties, we can enable control properties with PID controller. And in PID controller we have three proportions: proportionality parameter, integral parameter, and derivative parameter. But what I used is only a normal enabled one, and the mostly I have used this using the Lua script. As we can see, this is a script used for moving of a robot in a path planning for avoiding all obstacles. So now I will show you how we can make a visibility of this robot. See, the first 8 uh, blocks show the visibility, and the last 8 blocks show invisibility. Each and every box has a property of a layer. So we can see that if we click here, it shows it this as visible, and we go for this robot base visible, and we make it invisible. So we can see that this is the actual exact convex shape of the robot base. Hmm? This is a visible basis in a convex shape. So again I will convert this back. So similarly all the parts have been attached in the same way. So for in this robot, there are we can move the whole robot to center. By using translation properties, This is in the Z direction. We can go for XY direction also. So you see the robot is moving in the Z direction. But we can change this by going into tools with object manual manipulation settings, where we can select the preferences between Z direction or XZ direction, where the robot moves in the XZ direction, or we can go for XY direction, where the robot moves in the XY direction. And we can also move the robot back to its in Z direction and place it on the floor. So here we have 4 revolute joints. First revolute joint is the left motor. Then the second revolute joint is the right motor. And there is a revolute joint for the holder. As we can see here on the holder, we have a revolute joint which connects the steering of the caster wheel with the base. And there is also another revolute joint which is basically visible here. We can make it as an invisible one to the front wheel and the holder. And the design considerations which have been given in the Vrep tutorial itself. The first is that we should consider pure shapes. Pure shapes are basically shapes which can be made in Vrep itself. But this is a complicated shape which cannot be made in Vrep. That's why it is being converted into a convex shape. And convex shapes helps in using in dynamic simulations. So what we have to do is that convert a normal shape into like let's say we are converting we'll add a primitive shape like a cuboid which has this one with this. Let's say this is a cuboid we have added, and we'll convert this into a convex shape by using edit morph into convex shape. So this is a convex shape, and again we'll take the same cuboid, we'll create another cuboid and create a cuboid of the same dimensions and press it OK. So both the cuboids are at the same position. It's the same case with the base, visible base and the robot, the right wheel and the visible wheel, the left wheel, the holder and the visible holder. So what we are going to do is that this convex shape we are going to make it is as invisible one.
Difference.
And there is a difference in the convex shape and the STL file. The STL files are
Egg
like are of this kind of shape, and the convex shape are of like an egg kind of a shape. So in this is a pure shape. That's why there is. So here we have a convex shape and a visible shape. So we'll make this convex shape as parent. We're going to edit and make it as parent. In this way I have created the whole robot with the convex shape, with the convex shape and the visible shape, the convex shape and the visible shape. So for connecting the base with the wheel, we need joints which are the revolute joints for the left wheel and the right wheel and the wheel holder, and the revolute joint for the front wheel. So by doing so we have created this robot. And here in these slits we can also use sensors We can also add sensors to this robot and create it into a much better one. This script is being used for path planning technique. Now, now we have seen about how a robot is assembled. Before going into path planning, we will see about local masking and global masking in dynamic properties dialog box. In dynamic property dialog box, all the local masks and global masks are ticked. But in IK or any other dynamic model, we have to select alternative four square tick marks so that all the bodies are in alignment, and there will be a smooth simulation will occur, or else the robot get dismantled, and there will be collision between two or both convex shapes. And in dynamic rigid body dynamic properties, we can also see here the body dynamics. We can increase and decrease the mass of the particular part of the robot. We can also change the movements of mass, which increases by in multiplication of 2 or division of 2. We can also compute mass and inertial properties of the convex shapes directly by using this, and giving the amount of density required for the body. For if you give 1000 for density, then the mass changes here, and the moment of inertia also changes. We can also the automatically calculated inertia mass matrix divided by the mass m by m power 2 is shown here. The position of the center of mass is also shown here. Now we'll go into path planning. This is the environment that I have created for a mobile robot for path planning. For before going into path planning, we'll see what is how to create a path. So I'll just show you the stimulation how this robot works and reaches its destination point, that is here, and the start position of the robot is here. These are all the obstacles which are not moving. We can give different speeds, or we can use the formula of the differential drive robot in the script for calculating the speed of the robot. The distance that he is showing here in this video is the distance between the obstacle and the robot. This is the path in which it is traveling, and we can also see that a violet color line is being traced. This is the trace which we will be learning afterwards in the graph how to do so. This path is automatically calculated using the path planning module. So we'll go for the path planning module. Here in calculation module, we have path planning module, where we can add a new object which is holonomic or non-holonomic, depends upon the robot we are taking into place. So but here we have taken here as a non-holonomic robot because in non-holonomic robot, it cannot move in all directions freely, but in a holonomic robot, a robot can move in all directions freely,
More number of degrees of
and it has more number of degrees of freedom. So this is a non-holonomic robot. Here a associated dummy is being used. Here the dummy is basically the robot. Hmm? Because this first we are connecting the robot to the target position here. So in path planning, this non-holonomic is the robot. So robot is a dummy. As we can see it here in the scene hierarchy, robot is a dummy, and under the robot dummy we have the actual robot present. So we can select here as the robot dummy and press OK. And this is a gold dummy. Gold dummy is present here. We should actually add another dummy by going here, add, and add dummy here using this add dummy option. Then go for goal dummy, take target as a goal option, and the path object is actually a path. So adding for this path object, we have to go on the floor, press right click and add a single path which is given, which is a path. A path can be a segmental one or a circular one. Anyone is possible. We just have to select one path. So we'll take a segmental path. So this is path O, for example. Then we can so go for search parameters. The search parameters are nothing but this blue color line box which shows the area in which the path has to be calculated
Not yet on
in
this floor.
on this floor. So this area can be extended or reduced to according to your requirements. And here also shows the amount of angular step size. We can change this. Minimum turning radius of the robot can also be changed. By using this, the path planning module calculates the robot calculates the path from the start to the target dummy. So how we will place all these obstacles? Now, before completing the path planning module, I want to explain something about the collection module. So for the collection module is one where all the cuboids or obstacles which I have placed on the floor are collected and added as a single entity. This has, and we are adding all the objects and excluding the robot here. By doing so, the collection module accepts all each and every cuboid as a single entity other than the robot itself. So we'll go back to the path planning, where in our path planning the collision object distance, this we'll see later. We'll see in this we are seeing that what is the minimum distance the robot has to maintain between the obstacle and itself, and the minimum and the maximum distance or the just obstacle collision. And the robot should avoid the collection. The robot is the robot visible base shape actually, and the obstacles are the collection. By doing so, uh, we have told the algorithm used in the path planning module that the robot should avoid all the obstacles which are under the collection module. So the robot will start avoiding all the keywords in the environment. This external is a wall which avoids the robot to fall out of the
Floor.
floor. So now we can see, now by clicking on this one which is previously present, we can again compute different paths. This is another path, this is another path, this is another path. This is also another path, and the robot will travel in that particular path. The robot moves in the calculated path. We can see here the robot dummy is following the path, and the robot is following the robot dummy. And we can also see that it reaches the target dummy which is present at the end of the path. This is at the end of the path, and it is avoiding all the obstacles. Now, as we have seen how a path is being planned and a robot moves in its path, we will see how to plot graphs. Here I have, for plotting graphs, first you have to go and add a graph. And here in the scene hierarchy we can see the graph here. We can rename it as force 1 or anything as you like. Here in graphs, here this is a buffer size. Before going into buffer size, we will see we'll add a float view. In this float view, we'll add the graph. Associated graph is to be added. This graph has a black screen, which we can change this black background into any background as required. You can see the colors are changing. White background, and since it is a white background, we cannot see the decimal places
Grid.
or the grid here. So we'll change the color.
Again, sorry.
Here when graduation grid, where you can see the color changes to black or blue or any color as you like. Here we can add using data stream recording list. We can see different position of in x of the object, position of y, or rotation, angular velocities, proximity sensors, vision sensors, force sensors, and all other ones. We'll go for uh, collision time calculation. Object is overall time and place OK. Now we have to increase a buffer. Buffer is something which says that the which in which the time required for the robot to move from point A to point B, it changes every distances from x from the start position to end position. If the buffer size is very low, the graph does not take the total simulation time. So we have to increase the buffer size to something. So well we see, as we can see, the robot is started simulating here, and we can see the time graph changes. But while we come out, we have to zoom out to know how from what time it takes. You see, if the buffer size is very low, the time in x does not start from 0. It starts somewhere at 67, 6.77, which is not a good thing. So we have to increase the buffer size to something large, as let's say I'll put it here 3000, and we have to use trial and error method for finding the exact amount of buffer. Let's fast forward this by using this rocket, where the robot will go in a faster pace. Here the robot is starting at zero position, and is ending at 7.72 seconds. This is the total time for required for the traveling of the robot from its start position to its end position. As you can see, I have also added other graphs, which are force graph, trace graph, and velocity graph. Trace graph is actually shows about the XYZ directions, XYZ coordinate position of the robot at each and every instance. Here we can do this by adding in position, absolute position of x, absolute position of y, and absolute position of z. This and this violet line is the trace line, which we can see as the robot is traveling from start to target. We can change these values for raw, derivative, integral or cumulative.
Velocity की acceleration is not.
In velocities there is no acceleration.
Velocity and
We can add velocities also here separately for absolute x, y and z. And for the robot you can say it as a robot base, robot visible base. And okay, we can change this one here as velocity, and we can change velocity into acceleration by selecting derivative. So here we can say that there is no acceleration here. So by selecting a derivative we can change velocity into acceleration. And we can multiply the value here for derivative based on the mathematical equations. And we can see other graphs. I have put these other graphs on the other scenes here. This is a velocity angular wheel velocity graph, where velocity of each wheel, you can see here the left wheel and the right wheel. It starts from 0 and ends at 62. This is for the present. This graph is for the present simulation what we have done. We can see it again what happens. You see, if the wheel velocity reduces and changes, it goes down. And if wheel velocity if there is any turns, we can say that the robot is turning or the wheels are turning by seeing this graph. Here we can also say that it starts from 0, and as the robot stops, the wheel velocity reduces to 0 position on the y-axis. This blue color indicates right wheel and red color indicates left wheel. So we can see that both the wheel velocities sometimes are equal and sometimes are varying towards negative and positive. We'll see another graph which says about the time graph or the acceleration graph, which we have done now. There is other graph which says angular velocities of the wheel. This shows the angular velocity of the whole robot and in total simulation time. Here we can, this is the highest point of angular velocity. You see there are much higher angular velocities coming, that is 3.3 and 33.9. And by using any other graph, we can also add any other graph if needed. More graphs also can be added, and in one single graph we can add more than one quantity, or and we can rename it as required. And there is another good facility in Vrep, that we can export the particular graph into CSV, which we can open it in Excel file. You see, for force sense, let's say for this force, I'll export it into CVS.
It's 4:15.
And all the values we can see here, the time, the exact time, and the left wheel acceleration and right wheel acceleration. See, this wheel well acceleration is negative, means it is rotating in the opposite direction, and this is rotating in another direction. From this we can conclude if the robot is moving turning towards the right or the left. So but this is the force graph. We can say how much force is acting on the wheels. Like a negative force implies it is acting lesser force in the opposite direction.